Okay, so this brown bag will just be an overview on Kalman filters and kind of an introduction to how we're using them on our team, and just hopefully build somewhat of an intuitive sense of what's going on. And then if you're really curious, you can dive further into the math or different variants of kind of a vanilla linear Kalman filter and other links online. Okay, so to take a few steps back from a Kalman filter, we want to first think about like why we are using this, and we're using it for our state estimation team to try and get an idea of like where the vehicle is and kind of help us map out and navigate the surrounding environment. So from like a fundamental level, go through kind of a quick history on how we've gotten to the Kalman filter. So first off, let's imagine that we're trying to go from point A to point B. Maybe we're in a ship, we're trying to cross the ocean. So first we might want to know our direction. And previously, people would have used like a compass as far back as like 200 AD or as sailors and stuff. And then we might want to know our position. So people looked into the sky and were using all kinds of different like ways of measuring your position relative to other stars and stuff like that, and then using that to help map out where you're going to go on this map. Additionally, then, we might want to measure our speed so we know how fast our boat's going through the water. And like for sailors, originally this is done by measuring the knots on a rope. So as you throw a rope out, and then as the knots pass through your hands, the time or the number of knots that pass within a certain time tell you how fast you're going with the boat. But of course, then you need a good way to measure the time as well. And so you can get a rough estimate by using a sundial, which is what people first did, and then other ways of measuring time with like an hourglass or like a grandfather clock gave you like more accurate and smaller increments of time, but still not super helpful if you're on a boat in the middle of the ocean. You need a really reliable way of measuring your time so that you know how far you've been, you don't get lost. And so the invention of a chronometer made like having a handheld stopwatch like possible, and that really made navigation in general possible. So a very common approach for navigation is dead reckoning, where you initially we initially have our direction. Now we might use like a GPS or something to get that, but we know like our general heading, we know our general position, and then given our measurement of speed and then our measurement of time, we can figure out how far we've traveled and in what direction from our initial position. And then from there, we know like where we expect to be at some next point in our travel. But or then we do it again. But there's a significant problem because a lot of the noise in these different measurements can build up. And with dead reckoning, there's really no way to correct like previous error in measurement. So it just continues to build until you get further and further off course, and eventually maybe you get lost in the middle of the ocean and think that you arrived at one side of the world when really you arrived at the other. And these error can be in position, or it can be in your heading, it can be in the distance, or because of like you don't know your speed or you don't measure your time well. And so in order to do more complicated things, to navigate not just oceans, but like in the space race, trying to go from Earth to the moon, we need to combine our predictions of where we think the system's going to go with our measurements of where we like detect our system actually being. And in like the 1960s, this was especially important as the US is trying to put like the first man on the moon. And so very brilliant man named Rudolf Kalman, who unfortunately passed away a couple years ago, but came up with this idea that used statistics to combine an estimate of the like system as like a prediction with a measurement, and modeling both of those as Gaussian as measurements with Gaussian noise. He like reasoned and kind of developed an algorithm that we now call the Kalman filter that optimally combines those two in like to minimize the mean squared error over time. And so that ultimately was a like significant thing that enabled the Apollo 11 mission to get to the moon. All right, so there are a lot of ways to make the Kalman filter really complex for complicated systems, but we'll just take a closer look at like a simple one-dimensional case where this will be us and we're going to be walking down this line. And this will kind of go through and hopefully build some of the intuition behind how the Kalman filter is combining these two, the Gaussian noise between the measurements and then the prediction of where the system will go. So if we're walking down this line and we like close our eyes and keep walking, we might have an idea like where we're going to end up. So we might know how many steps we're going to take, and we say, okay, well, I think I'm going to be at this point down the line. But we might not be entirely sure, and so we might say that instead of having this exact certainty in where our next position is at like our next step, we're going to have in this case, we'll just assume it's a Gaussian distribution where we have the mean centered at where we believe we're going to be, and then some variance of uncertainty in that prediction of our mean. And so that would be like our state prediction. And then in addition, maybe we can use a sensor. And so the sensor might say, right, report a single value that says, okay, the sensor believes that you're here. But of course, we know that the sensor might have noise in and of itself. This could be like vibration, it could be electrical noise, it could just be like the sensor's own inherent measuring ability that's holding it back. But regardless of what it is, we know that there's going to be some kind of noise in how the sensor's going to measure our position. And so we'll treat that one as a distribution as well. And so like right away, it's kind of apparent that, well, these measurements don't exactly match up. So which one do we trust? And we can use this variance to help us do that. Because we're not entirely sure if we want to trust our own prediction or the sensor. We can use the uncertainty to kind of weigh the two between each other. So if we notice that they overlap here, we could think that we could make a new distribution that like covers the overlapping section, and then we'll use that as like a better estimate of where we think that will be. So this kind of like trades off our own high, like low uncertainty in our estimated prediction with our like maybe high uncertainty in our sensor prediction or sensor measurement. So in order to calculate this distribution, I guess I'll take a step back. We'll get to that in a minute. But basically, we get this best estimate of our position, and then we move forward a step. And then we kind of take that best estimate and then say, all right, that's going to be what we'll use for the next reference point going forward. And then we just do that for the next k step, the k plus 1, and so on and so forth until we arrive at the moon or wherever we're trying to go. So a couple assumptions then to take into account from what we just talked about is that we're assuming that there's Gaussian or normal distributed noise for the measurement and for our system, for our process. We're also assuming there's no bias in terms of this measurement. Like we're assuming everything is centered about a mean. And then we're also assuming that these distributions are independent of each other and that we're using a linear system. So it sounds like kind of a lot of assumptions, but the result is that this algorithm is really fast, and it can do a lot of the computation internally. So you don't need to have a whole lot of computational resources, which is really important, especially for like embedded system applications like robotics or like rockets or something like that. We can also combine some of our sensors together, and all of this ends up being an optimal least mean square error estimator. And if you're not entirely familiar with how like least squares or mean square error works, there's a wealth of resources online, and we can help you look more into that too. But given those assumptions, there's also ways to make the Kalman filter more complicated. So of course, most systems are not linear. And so if you're dealing with something that's really nonlinear or you want to be more accurate, maybe you can play some tricks to incorporate that nonlinearity. into the model, the Kalman filter model. So the first one is called the extended Kalman filter, where you take the state that you're originally at, and even though you have like a nonlinear prediction and maybe nonlinear sensor measurements, you linearize about a certain point and then use that to make your next prediction for the future state. Now, if the state is really, if there's a lot of time in between those two, then this estimate might be very poor. And also if the system is really nonlinear, then it might also not perform very well because of course you've linearized about something that is going to be changing a lot. So that's one approach. A second approach is called the unscented Kalman filter, where you take your distribution of like the estimate of where you're currently at, and you pick a set of what are called sigma points within that distribution. And you transform those points through to the next state, and then make a new distribution that includes those points. And in practice, this is usually better than the extended Kalman filter, although you usually want to give some good thought as like a, I guess, Kalman filter designer. This is something that you'd want to give some thought before you just go off and implement one without thinking. It's also worth pointing out that there's a whole lot of other variations. Those are just two of the more popular ones, but there's a lot of resources that you can read about different variations on them. All right, so hopefully we have a little bit of intuition on how we're going to be combining our prediction with our measurements to make a better estimate together. But what does this look like in practice? So we'll go through some of the math just so hopefully, like, if you do read some more of these resources, it's a little bit more approachable. And then you also need to know the math in order to actually be implementing these, or at the very least know how to detune other implementations that you'll ultimately be using. So first off, we need to make a prediction of the next state. So this is our first prediction of how many steps we've taken. We take our current state vector and then a transition matrix that basically tells us, like, if we are moving at this velocity and we travel for this amount of time, where will our next position be? Something like that. Then we also might have control inputs and a matrix that maps those control inputs into the actual state that we're moving. So again, if we're, for example, in a car and we step on the throttle, then how might that impact our future position? And then we store these in kind of a temporary state vector. Similarly, we also want to compute our uncertainty. So this would be like the variance or covariance in matrix form. So we take our previous uncertainty and then of like the like the current state, if you will. And then using that state transition matrix, we propagate that forward and then combine it with our like process uncertainty. And that's the uncertainty in like the system itself. And then I could store it in a kind of temporary uncertainty variable as well, and you'll see why in a minute. Then kind of kind of like between the time step of making this prediction and actually like finding that best estimate, we need to read the sensor measurement. And so just try to remember that these variables are Z for the sensor reading, the measurement uncertainty is commonly denoted as R, and then there's a measurement transition matrix that maps the sensor measurement values into the state space. You can imagine that maybe your sensor is measuring things on a different scale than you actually want to be comparing it to with your state. Maybe it's measuring it in centimeters, but you want to be using meters, and then you will need to be able to convert back and forth. So that's what that does, and you can get more complicated than just centimeters to meters, but that's kind of a simple example. So now we have effectively our predicted state and our measured state. And so we want to combine these two. And the way that we like combine these two is we effectively multiply these normal distributions. So with our one-dimensional case, both of these normal distributions have this equation that maybe you've learned from statistics courses. And when we multiply them to and work through the math, we end up with a term that we can factor out that like balances the predicted variance with the measurement variance, and that value is called Kalman gain. And so the Kalman gain acts as a weight between the mean of the sensor and the like the mean of the measurement state, and the predicted state. And then it also acts as like an additional term in finding the variance, the ultimate combined state. And so there's another good blog. There's a really good blog post that walks through how some of these equations work. So I'd highly recommend you check that out if you're interested in breaking it down a little bit more. But for the sake of time, keep going. The main concept here is just to know that we're combining these two normal distributions to find a common gain, and then we're going to be using that common gain in order to find our ultimate mean and variance uncertainty, covariance uncertainty of our combined distribution. So kind of a high-level takeaway is what this common gain is actually doing. And so the common gain is effectively like a fraction. And so when it's 1, that means that our predicted, like the covariance of our, or the uncertainty, I guess, of our prediction is very, very high, meaning that the sensor doesn't matter as much in this like fraction. And so what that means is that our sensor uncertainty is very low, and so we're going to fully trust the measurement. And then that ends up affecting how our mean and variance are ultimately calculated as. And when the common gain is pretty close to 0, that means that our sensor variance is extremely, extremely high, meaning that we don't really want to trust that because it has a lot of uncertainty. And so then we're going to be trusting our prediction more. That's kind of like a just general understanding of what's going on there. So going from our 1D case into our matrix case, we're going to incorporate this additional measurement transition matrix term H that we talked about, as well as R is just effectively going to be our measurement noise. And then you kind of notice like a lot of these equations are might look more intimidating, but they're really the same things that we were just talking about. So I was like the mean of our sensor distribution is just the actual value reported by the sensor itself, and then the prediction of our, like the mean of our prediction is our predicted state just converted to the sensor measurement space so that we can compare it to that measurement. And then the common gain weights to 2. So weights to 2 before they're combined with our like kind of calculated predicted state. And so what we end up with is the resulting mean, the resulting uncertainty of our like best estimate of the state after we're combining those two distributions, the predicted distribution and then the measurement distribution. So all together then, what we're doing is we're first calculating the like predicted mean of our next state, and then doing the same thing for our covariance uncertainty, accounting for the noise that we expect our process, like our system, to just inherently have. Then we read these sensor measurements and then take those kind of intermediate values and then calculate a common gain that effectively trades off the variance in our predicted and measured like means, or yeah, it uses the variance of those two values to weight this gain between 0 and 1, and then we use that to finally make a best estimate that combines those values into our like final combined mean and uncertainty of the state. And I guess one little minor note, if you notice values with like this, or variables with this little hat over them, it's because kind of an estimated value. Like x of k without a hat would be the true state, and x of k with the hat is our estimate. So it's important to note here that this is really our best estimate of the system, because maybe theoretically it would be impossible to know the actual state, but it's helpful to still designate that this is an estimate. So then at a higher level, the way this works then when you're actually implementing it is that you make this prediction first. So you run these two equations, you get your sensor measurement update, and then you pass it in to the rest of your update equations in order to calculate your best estimate going forward. And then your system progresses one time step forward, and then you repeat the whole process. You predict and then you update again. And some additional remarks here to make are that you want to try and use reasonable values for your process noise and sensor noise. They don't have to be perfect, which is one nice thing about a Kalman filter, but they should at least be like reasonable so that you're eventually like balancing the model with the sensor noise well. It's also important to make sure that you're matching your time steps in your model with your actual update rate, or else you'll just be off, and it's a relatively easy, well, sometimes easy thing to do. The Kalman gain should also converge. So if you're like trying to debug this, eventually the Kalman gain should converge to like a certain value that'll kind of weight the average performance, if you will, of your measurements or your predictions. And then if you're interested in more information, there's a lot of links in these speaker notes, which are always in our drive. Like the PowerPoint's always in our drive, but I can send those links out later as well too. So on our team, this is how a Kalman filter like works in simulation. So in the top left, we have a little car that's driving around in a figure-8 loop. And then on the right, we have our position. Then on the lower left, we have our velocity. And then on the right, we have our heading. So probably the one that makes the most sense intuitively is the position. And so we're starting off here. And then green is like where we're starting off right here. And green is where like the model actually went. So this is like where in our computer we tracked it going. And then there's some noisy measurements that are just sort of introduced into the system. And then blue is kind of how we're combining those values and then making a better estimate than just following the noisy measurements or following the model on its own. And so if you're interested in practicing with some of this yourself, there's a tutorial on our GitHub. Highly encourage you to check it out. There's the code in there, and you can run that and experiment around with it. And what's something to note there is that it's basically just a constant velocity model where there's just a singular velocity signal and then a lot of measurement noise that's sort of bouncing around. But what we can see is that our Kalman filter is able to estimate like a reasonable approximation to that true velocity. And this is all without knowing what that true velocity signal is. This is only knowing that our system model is like kind of expecting a constant velocity, but this is still able to cut through all of the noise around what our model actually is, so to say. It isn't using any control inputs, but you can vary the process noise, it's like the noise within the model, and the sensor noise in order to kind of see how it affects like how quickly it can, where it converges to, and things like that. In either case, you should eventually see like the uncertainty start to go down as it does converge, and again the Kalman gain should also decrease, or at least converge to like a single value that means that you're tracking the system reasonably well. So with that, I'll kind of leave this slide up, just kind of have an overview of everything. But if there's any other questions, I would love to answer them or talk about any of them more. Thank you.